Hello, Krishna, I'm audible.
Yes, sir.
Okay, yeah. So, Krishna, in the last class, I taught you about Lorentz force. Yes, so you are clear with the concept earlier, please discuss, like Lorentz force and the previous things we had discussed so far. Oh, yeah, Krishna, do you have any doubt in the previous topics?
Yes, sir.
Which topic you had doubt?
I don't have doubts.
Okay, you don't have any doubt, right? Okay, so I'll actually move with the next topic, that is Hall effect. Actually, Hall effect, I'm not sure whether this is part of the syllabus or not. So, mm, I don't know, like whether this is really part of the next syllabus or not. Check once. Yes, I think so. It is a part, so I'll just take it little bit. So yes, assume you are having a conductor, container. It's not a conductor, maybe. Okay. So look, wait, now this kind of surface, basically, a kind of conductor is given to you. Okay? Then what will happen is, just think of it once. This is basically a conductor. Okay. This conductor has, you can just call this width, that is W, and total length is given as H. Let's call this as L, and height is given as H. Okay? This is given as H. Now, I'll just explain once. Assume I'm providing an, uh, this is a complete circuit. Okay? this is basically complete circuit. I have just completed circuit over here. This is potential. Now you know if there's a potential, there will be some flow of electrons, right? So basically current will be flow. You know how the current flows. If my current is flowing in this direction, my electron must be moving in this way. So because this is for positive side, this is negative, so current is going to flow in this way. I can simply say in this conductor, all the electrons are trying to move this side, right? Just think in this way. Now what I'm saying is, so all the electrons are actually moving this way. Now think one more concept from here. Assume this is electron moving in this direction with velocity. Okay, in this whole conductor. Now I'm saying there is a magnetic field in this whole thing, in this whole conductor. In which way the magnetic field is in this way. Okay? In this plane, magnetic field, perpendicular to it. Okay? Perpendicular to it. You can just think of it. This is your, okay, right? Yeah. From here you can think this is your x direction, right? This is your y direction, and this is your outside is z. So you can now say that this magnetic field is in minus. You can say negative of z, which is inside. Okay. If I put here, this is inside the plane. Okay? This is magnetic field. So Krishna, can you tell me if this electron is moving, what is the direction of? Because look, right now your electron is there. It has some velocity, right? So can you tell me what will be the direction of force on this electron? Kirtana, just let me know the direction of force on this electron right now. Kirtana, please let me know first. What is the direction of force on this electron right now?
Z direction.
Which direction?
Z.
I can't hear you properly. It's like just some beep.
Z, sir.
Uh, no, I can't actually get you properly. Which direction? Be clear once.
Z direction.
Z direction. How it is going to be in Z direction? Just think it once. Your velocity is in X direction, right? Your magnetic field is in minus Z direction. So why do you think that? Just calculate once again. What's the direction of
Negative Y, sir.
which direction? You can't even apply
Negative Y, sir.
negative y, right? Makes sense. So this negative y is going downside, right? Okay, do you really think this is going to be in the negative y? Just think it once. I told you whatever the way right hand palm rule and whatever we are applying, that goes on, that gives the direction of positive charge, right? This electron contains negative charge. So whatever you are getting due to that positive, just put a negative when you are looking for the electron. So in case of positive, you are getting downside, but for electron, you are going to get negative. Okay, by formula, I can explain you charge V cross B, right? What is B right now? That is minus K, cross of I. Okay, so you know that I, J, and K, right? I, J, and K. So you can simply, in this particular case, you can say that just K is minus of K, right? So I'll put the whole negative outside. Right now, just keep outside. What is K cross I? That gives you J. So you have got something like F is equals to minus Q times of J direction, right? Now you will say that the answer is minus A. No, because you are having an electron. Electron has a negative charge. So put minus E, this minus becomes positive. Direction is J. So direction of force on this electron is upside. Force. Force. What is the direction of force? Upside. Okay. Force. Now, if you see carefully, what will happen? All the electrons will get pushed towards upside. Understood that? So you know Krishna, what's going to happen? Because the force is applied upside, even though all the electrons were there, when they are going to push at the top, right? When this electron reaches at the very top surface, I can say here, like from here, right here, on the surface basically, even the force is applying at the top right now, it can't move further. So you can say at the top, the density is going to increase, right? If this is going to happen, then what will happen in that case? You can say when the density is going to increase after a certain time, then due to this force, there will be some magnetic electric field, right? Because negative charge is upside, so density is increased at the top. At bottom, you will say most of the charge are either positive, either there is no charge. So you can say it generates an electric field upside. This, right? This is your electric field. Understood? Now you know if electric field has generated, you can simply say it is looking like one plate is top, another place is bottom. This is negative charge. This is either positive or uncharged. So you can say electric field is there. Wait, if this kind of situation is given to me, can I calculate the potential difference between this? Yes, I can. What is the potential difference? Isn't it looking like a capacitor? Like one plate is negatively charged, another plate is positively charged. This seems like this, okay? So in that case, what is the potential difference? That is nothing but total charge. With this comes out as electric field multiplied by the distance. Right? What is the distance between them? So you can simply say electric field right now, I don't know. Distance is given as height h, right? This is your voltage. Now what is electric field? If I ask you what is the electric field, this electric field is due to the this electron density, right? Now my task is to calculate electron density. How I can calculate? Also, you know that this just think in another way. I had a charge. It was moving with velocity. If in general, when current is passing, with what velocity your electron moves? It moves with drift velocity. Right? Electron is moving with drift velocity. Force is upside. Okay. So and their magnetic field is inside. Right? These things are there. Right? Okay. So Ketna, now if you see carefully, there is electric field in this way. If you have a charge, right, in presence of electric field, this electron will get a force downside. Right? What is the force? Force on due to electric field will be nothing electrons E. E is it the upside, and this is negative. So the force on this will be downside, right? Let me just remove everything from here. Force on this was magnetic force. Here it is F is equals to E times of this. This is the force on this electron downside, right? Is that clear? So if you just solve this equation, what you are going to get? What is the FB? FB was nothing but EVD times of what is it? B is equals to E times of B. So cancel. What you have got from here? You got the drift velocity is equals to E by B. Okay. This is the formula for drift velocity in this case. Because what will happen? Look, I'll explain you once more. Let it be. Look, earlier there was no charge. Okay? It was very simple. Nothing was there. What you did is you started some current. So when current started flowing, there was some electron which was moving. Because there was some magnetic field in that plane, there was some force. So initially, only force was there, only F3 was there. So charge starts collecting at the top. Assume in a very slow manner, charge starts collecting. But there's a time when enough charge is collected in the top and magnetic electric field becomes weak. Okay. Now, in this case, more charge are trying to do the same. But right now, what happens is on this charge, magnetic field is in this. What about the force? Because that's an electric field. Right now, this field has that's an electric field. So electric field is upside, but this is electron. So force on this will be downside. Active. So even though like when even single charge gets settled at the top, there will be some electric field. But until unless your magnetic field becomes equals to electric field, look, if this charge will straight be moving upside. Assume that initially electric field was zero, electric force was zero, magnetic force was some value maybe b. So it was going upside. Then it increased by a little bit margin, but still this is greater than this. So still it is moving still. When it want to move, the moment they becomes equal, they want to move upside, right? The new charge want to move upside. It means it will get undiluted. After this, because no charge is getting settled upside or downside, this is an equilibrium condition. Okay? At this point, you can say there won't be more charges settling upside. Okay, so if at this condition you had magnetic this drift velocity as e times 50. This is the relation we are taking right now. Okay? Understood this one? I think so.
Yes, sir.
Now, because if you see carefully, these two plates now can now act as a potential difference because this plate has some negative charge, and this might or might not be having positive or it can be neutral. So you can say you can calculate this is going to act as a battery. How? What is the voltage at this point? Okay, I can make it to this one. Assume now I am joining a wire. This is one wire from this plate, and this is another wire from this plate. Okay. So this is a negative, this is positive because this side is positive, right? Okay, what is the voltage at this point? Sorry, which voltage is there? Yeah. Let's keep it from here to here. Yeah. So what is the voltage over here? You know this voltage is nothing but electric field multiplied by the height, right? Whatever the height is there. Whatever the height is there. So right now height is h. So this is the small formula you are getting from it. Even though you can actually make it bit more. What is that electric field? What is the electric field value? That is nothing but V times of VD. So you just put it from there. E is nothing but VDH. Okay. Yes. I hope this makes sense. Right. Now in general, we say what is drift velocity. Drift velocity is nothing but the velocity with which this electron drift towards the other end of conductor, right? So you know that the current which is flowing inside. What is the formula for the current? The current is nothing but ANEVD, right? So from here also you can get the formula for VD. What is that? I. Okay. This A is nothing but the area of this cross section because where it is moving. So this VD becomes I divided by area, number density n divided by electron. So if you go and put this thing, what you're going to get? B multiplied by I multiplied by height divided by area. What is the area right now? If you see this area is equal to width into height, right? So W into H. Right? This is when we are getting into N multiplied by this. H got cancelled, so BI divided by NEW. Okay, that is another formula for this. Is that clear?
Yes, sir.
Uh, and one more thing, like this is okay. I hope this might be clear to you.
Yes, sir.
Now, what can happen is we can have different kind of motions in these kind of plane. Okay, basically these kind of situation we can have multiple situations. So I will explain a small concept, but basically it's not small, quite big. The next part is cyclotron. Okay, I don't know like whether right now they have this thing in this syllabus or not. Earlier it was. Okay, look, if you are very clear with the concept, you won't be having any doubt. Okay, it's very simple thing. So for this, I just wanted to recap you with a very small concept. Basically, what cyclone does is it accelerates the charge, accelerates the charge. Okay, it just provides acceleration to the charge. This is what it does. That's it, nothing else. So how it does? Assume you have a tube like this, okay, and there is some electric field in this. Maybe like this. It is going like this. Now, if some electron comes up, maybe I can call this as Q. If some charge comes up, what will happen? Because this is charge, so there will be force. What is the force? That is Q E, right? The force on this will be Q. So force F. So what is the F? F is nothing but Q times of Q. You know, if this is a charge, it has some mass, right? So you can say mass into acceleration. What is the acceleration it is going to get? Q E divided by M. Okay, this kind of thing will be there. Understood? So if you see carefully, if I say the particle started from rest, it initially does not have any velocity. If you keep a charge over there with the velocity, initial velocity 0, so v square minus v square is equals to 2as. If it covers some distance s in this region of electric field, what is the velocity? Velocity it will be having v is equal to initial was 0, 2 into a. Acceleration is nothing but 2e by m times s is the distance, so under root. This is the velocity it is going to have at the end of the graph. Okay. So these things we are going to use above it. Is that clear?
Yes.
These, yeah, these things we are going to use in this cyclotron. Okay. So that's why this is important concept. So yes, so what actually the cyclotron does is, so I already wrote over here that this helps to accelerate the charge particle. Okay, what it does is, it is basically used for the heavier particles, especially for the heavy particles. How it works? Okay, good. So just think of it that you have a spherical circle. Well, actually, this kind of circle is it fine? I'll just actually make it over here. Just a second. I will trace this circle once. The shape of it. This this is one point. This is one point. From here, I can try to trace it. So if you see now, I have this thing. Right? Let's merge this one. So something like this. Now I'm going to place it a little bit closer. If you see, there's very small thin channel, right? Maybe from this point to this point, a very bottom point. This time another will be from this bottom point to this top point. These are basic two halves, and this completes the whole of this circle. So how this thing works? Basically, we are going to provide one magnetic field. What kind of magnetic field? It can be either outside, it can be either inside. So assume there's a magnetic field inside in the whole section. Okay? A complete magnetic field. This region has a complete magnetic. Here also magnetic field is there. Now it's now what will happen is if magnetic field is there, okay, and if I ask you there's a particle which is going with some velocity, maybe let's say I'm saying there's a particle which entered from here, okay, with some velocity v. Then what you will say, sir, that if the particle has velocity v, it will go and make a complete circle, maybe like this, right? And will come out from this side. Okay, then what will happen? It will enter this because it has a velocity. Now, if I ask you what is the direction of velocity, this, okay, actually it is going upside. Force is upside, okay. So for this, actually, this kind of particle is needed. We have to take. Now, where we are going to keep the magnetic, what I can say, where we are going to provide electric field or magnetic field, electric field or magnetic field. Yeah, so you can say this is the center point. Bottom of the center point, I am making my particle to have electric field in this region. This is my electric field. And after this, I have electric field like this. Just think with a small pencil. Now, what I told is, just take a small random particle, okay, a random charge particle, and keep it here. Okay, right now I don't have any velocity because the charge is okay. Keep it here, okay? Sorry, it will go this way, but now it goes this. So it will go also. No, actually, wait a second. Wait a second. If I say my particle is getting inside from here, so yes, it will be having like this. Then particle is going from here to there. And it force here, then from here. Yeah, then that makes actually more sense. Okay, sorry. Here it should be like this, electric field, and here it will be like this. Now, it let's think in one way that you are having a particle Q. Okay, this particle is there. You know, initially because initially it was on the rest. So, what is the velocity? Initial velocity is zero. You have kept it in some electric field. Assume the electric field is constant. Why there's an electric field? You can simply say we have provided one this kind of battery. Okay? So due to this battery, there's some magnetic field. So because you are providing some magnetic field, the yes, you are providing some magnetic field. Let's make this initial velocity equal to initial is zero. There's some battery V, so this is going to provide some magnetic electric field. Now at this point, what is the force on the particle? QE. What is the acceleration? QE divided by m. Because of this particle, starting from here to here, assume this width was maybe h. Okay. So what is the velocity it will gain when it is going to enter this particle? How much velocity it is going to gain? V is equals to initial was zero. What we are going to get 2 times of a into whatever the h. Assume the length was small length was h. Okay. So V is equals to 2 times q e by m. You know, with this velocity, even though particle has initially velocity of zero, it entered from here. Okay, now it has velocity. So what will happen? Just apply your right hand palm rule. Okay, putting the thumb in this direction, all the fingers inside, so your palm will face upside. Mean to say on this particle force is upside. Here particle force is upside. It means it is going to complete a circle. When it comes, it is trying to come out of this place, this side. You can see the moment it reaches this point. Right now, if you know this magnetic field only changes direction, it does not change magnitude. Now you can say for this reason, the velocity of this particle is now initial velocity will be called as v. What is the new one? V square minus V1 square, this one, okay, this is V1 square is equals to 2. Acceleration is still the same because particle is same, right? QE divided by M. This width is also the same, so it will be Lx. So what is the new velocity? That is comes out as V1 square plus 2QEL by M. Now you can say this is new velocity. Now it goes inside, okay, and it completes the another circle, maybe like this. Although it's much better if you start from this side because after gaining, assume the velocity was here, so it went up, it came like this. From here, because it will gain more velocity, so here it is going to cover more bigger circle. More velocity, more bigger circle, right? Here it will come up like this, here it will complete a more bigger circle, something like this. Okay. So this is one thing you need to remember that because if you could remember in our circle thing, when we talk about completing a circle, what is the half mv square by r is equals to q VP, right? So here, if you see the velocity comes out as the radius it is going to cover, that comes out as mv by qv, right? More the velocity, more the radius it is going to cover each other. So v1 plus 2qe by ln, is it the same? Yes, it is. Yeah. So from here, I'm going to multiply. This. So the particle I'm saying right now, it did not started from here. It started from something inside, okay, so that we can actually make it proper. So from here it went up like this. From here it went and come up like this. If you see what kind of it is making some spiral, spiral kind of shape, right? So this kind of thing is going to. And if you see at every step, when it enters here, when it comes here it had here at this point it has zero velocity, went up this region, got some velocity, reached here. Again, when it had some initial velocity, got some acceleration here, got more velocity, bigger circle, and so on. Now, if you see, you will say, sir, it will enter at the end of the day, what will happen here? So, generally, this cyclotron we make to get higher velocity, right? So, I can simply say that there will be some exit point. Okay, maybe here it is an exit point. We will say after this particle is not going to move. Okay, maybe you can say from here you don't have anything. So after this, you don't have anything, it will directly move outside and you got an accelerated electron with a much higher velocity. Understood my point? Is this clear?
Yes, sir.
Okay. So this is what going to happen with this case. Okay. Okay. If you actually want more to be discussed about, so you can simply say at this part, your radius covered is R1. Okay. And this another circle it covered R2. For bigger circle, when it is here, it covered something like R3. Then after that, it covered here R4. Then after that, it covered here the complete is R5 maybe. And here it covered R6. Here it again covered R7. So you can see the radius is increasing, increasing, increasing by the time. Right? That's how these things are ongoing and on. So I hope the things is a bit clear to you. Kirtan, is this clear?
Yes, sir.
This concept clear, right? Okay, so this is about your this is just a simple concept. If they are asking you to calculate more things, you can actually go and do that part by yourself. Okay. So yes. Should I calculate something else? No, I don't think so. Also, if just have to tell you something, that the ratio of these radiuses, assume the R1 is some value alpha, then R2 will be, this R2 is going to be root 3 of R, R3 is going to be root 5 of R, okay, and root R, sorry, yes, the same thing. R5 will be, this will be R, right? Root R4 will be root 7 of R, and so on. Basically, this will be increased by root. That this is one increment you are going to notice, okay? So yeah. We can do small derivation for this, but it does not matter for us. If you are curious enough, you can try this derivation. Okay, and in the next class, let me know if you have got the similar result. If not, and you wanted to get the derivation, I'll explain you the derivation part also. Okay? So yeah, that's for the now. That's for the now. Any doubt, Keithna? Look, for this velocity part, instead of going in this mechanical way, what you can do is apply energy. Okay, that will be much easier for you to understand how. You know that there's a voltage V, right? Instead of electric field V, you can use voltage V. You know, when you put a charge in some an electric voltage V, so you got some potential. What is that potential? Two times of V. Whatever the charge is there and whatever the potential is there. So the potential is like Q2V. Okay. So this potential, what it is going to do is, this will be helpful for you, right? When you when you come out of this potential value, the whole potential will get converted into kinetic energy. So you can simply say, I'll start with a small derivation. Initially, you were at a zero, like your kinetic energy was zero. So you got this as potential. You got kinetic energy K1, okay? Minus final was initial was zero. So this becomes K1. So what is the velocity you have got? K, K is nothing but it is directly proportional to V square, right? Because kinetic energy is nothing but half and V square. So I'm saying that this is basically directly proportional to V square itself. So you can simply say this is nothing but V1 square. So by V1 square divided by some K, or you can call it as some A times of this. This A is a constant. Okay? This constant is nothing but you can say half and V. So this M by 2 value, if it's 2 by M, so this is, I'm writing it as a K itself. So this velocity comes out as this V1 square. So V1 comes out as KQV. Now what happens is, this particle is here. It started a new journey. So what is the radius you are going to get? MV divided by Q. Then after this, what will happen? Again, it completed one circle. What is the radius? That is R1. Okay, it got another energy. So what is the new energy? Potential energy QV, again same. In final energy, that is maybe K minus what is initial energy? KQB. KQ, and what is that thing? Again the same thing, again very same thing. But this time you will get a more energy. Okay, initial plus final. Understood? That is the thing you are going to get. So this thing is going to get added with you. The whole thing is going to get added with you. Okay, and again you are going to put a new whole square over there. So that's how you are going to get that result back. So yes, Kirtana, let me know if you have doubt or not.
No.
No doubt, right? Okay. Yes, so I think this part is more than enough. Alright, Vedna. So next we can discuss about magnetic. Look, Vedna, look. Earlier what we have done so far is we started with the thing by saying charge was at rest. When it was at rest, it was providing the electric field. Makes sense. I started moving it, it provided me current, okay. It had current, okay. So after this, we moved to the new chapter and we said if charge is moving, okay, it is providing some electric field, basically magnetic field, right? Then we said if there is a magnetic field, but this charge can also move inside a conductor, right? If multiple charges are moving, they all are going to generate magnetic field. So similar way here, after this we studied that if we study the charge is there, which is having velocity, if it is moving inside a magnetic field, that's a force on it. Right? Can I say if another current conductor is there, this conductor is there moving inside this way? Okay, there is an electric field which is inside, right? Inside the plane. You can say magnetic field inside, velocity is inside of the charge. So can I say charge particle will experience force upside? Yes. This will also feel upside. Yes. This will also feel upside. Yes. Okay. So you will see, but so charge particle is very small. It won't make a thing. But wait, this conductor contains billions, millions of the charges. Can I say that this millions of charges are going to provide net force upside? Yes, it is going to do this. Okay. So let's see how this is going to work. Now you must have got a very small idea. Okay, but I will explain you in like formula is quite the same. Okay, it won't be changing a lot. One way I'll explain you in a very simple way. Assume this is the whole of conductor. It's very thin, but I just made it so that we can visualize the thing. So assume there's a current I which is upside. Okay, upside. If current I is upside, I can simply say electrons are there, electrons are there, electrons are there, which are moving downside, downside. So what is current? That is nothing but d dq by dt. Okay, mod of it. Because we know direction is downside, so it is something like this. Okay, we generally whatever the formula we are applying q v cross b. If I simply go and apply, okay, let's do this thing for a very small single charge particle. So df, what is the force on electron? That is nothing but single electron multiplied by what is the velocity? That is dv downside. Let's say whatever the velocity it has, because this depends upon current, right? We will look at the velocity later on. So whatever the velocity is there, multiplied by the b. We know the whole thing is downside. Right? This is downside. Okay, makes sense. I have taken very small because I am going in the direction of current, so I am taking a small dl particle. Okay. If I have taken a dl particle, I will say because charge particle is going downside, I will take the velocity also as a negative. Why the velocity is taken to be negative? Because my this direction is taken as a positive. So velocity nature is negative becomes this. E V V. Clear? Okay. What is V right now? I'm not sure what is V. So I can simply say this V is nothing but change in position. So can I say this is nothing but E, this is nothing but dx divided by dt? Yes, velocity is nothing but change in position divided by that. Okay, here I have taken this. Let's of the overall length L. Okay, if I say the whole length is L, I have taken dl part. So here also dl by dt. Okay, d. Now if I ask you, now can I rewrite the same thing as what is this electron, right? Can I say this is nothing but the charge? So if I write in another way that d times of q, because this is a small charge dq, I am saying small force that is due to the small negative charge. So this is this thing. So it can be rewritten as dE divided by dt, okay, multiplied by dl Okay, multiplied by the voltage. What is dE by dt? This is nothing but change in charge per unit, basically charge by time, right? What is the charge per time? That is current. So what is dF? You have got I dL times of d. Okay. Is it the only thing? Yes, that's the only thing. That's the formula for your force. Now I just need to integrate it. If I just go and integrate this, what I'm going to get? Force equals to I L B. Okay. Now if I have to keep it in the vector form, this can be represented as F is equals to I, because this is a this tensor quantity. I'll put L cross B. Okay. If you say why just put cross thing, so you know this we can go in a vector form also. This was dq. Instead we can actually put now. It will be much better if I just go in a whole of vector form. So yes. You know force df is nothing but dq. Okay. Yes, dq times of what is the velocity times of v. So let's keep it as another v cross v. Right? What is dq? Let it be as it is. What is v? dl cross dq cross q. Keep this t outside. dq by dt dl cross d. Okay, makes sense. So what is dq by dt? Now you can keep it as I. What you are left with L cross d. Okay. So this df, sorry, this is just df. This is dl also. Yes. So integrate this. What you are going to get? F is equals to I L cross d. Okay. In better terms, if you wanted to say this F is nothing but I times of DIL sine theta, and I'm just suggesting the direction of force because we don't know what is the cross product of them comes out as, right? Or in another word, you can write this as L L vector into B vector, okay, divided by the magnitude of force L dot yes, L cross theta magnitude. This is nothing but the direction of this thing. Right? You don't have to get confused with this. So, Ketna, if you have any doubt, please let me know. Otherwise, we are done this with this small topic. Okay,
No,
no doubt, right? Okay, great. Now, this is one thing. Now, I have one more doubt. If I say that, now you know, right, what is the formula? If I say this is a current, it is this is the length of conductor, it is having current I. So, if I ask you, this is placed in some magnetic field this way, right? So, if I ask you what is the force, you will say B. B is magnetic field, B, current is going I, and what is the length? That is L. Okay, that is fine. Fine. But instead of this, if I say that the question, okay, let's frame a question over here. If the question suggests that this is a conductor, okay, this is a conductor, and from here the total length is maybe L. No, it is not this. Assume Kirtana, you had a complete wire which was initially in a frame of circle. Okay? It was a complete circle. So, no, not that way. Okay, makes sense. So, what I wanted to say is initially you had a wire. The wire is in a shape of this. This is one semicircle. Basically, this is R, and this is another semicircle. This is a complete wire from here to here, and there's a current I flowing. So, can you tell me if I keep this in a magnetic field, which is just perpendicular to it, can you tell me what is going to be the magnetic value of force? Kirtana, can you calculate this one? Okay, if you look, can you calculate this one? I'm just saying this whole length is L. Okay. So look, I'll explain you this way. Okay. Kirtana, do you know what is Polygon's law of vector addition? Could you remember about the Polygon's law of vector addition? Look, in that way, what we generally do is assume this is one vector, okay? This is another vector. So what we say, this A and B will resultant will be nothing but A to B, right? The tail of A to head of B. Okay, makes sense. Now, if I say this, I can say this is resultant of A plus B, right? Okay. Now I'm saying let's remove this A and B now because we have got the resultant of it. Now, if I say it now, if I another vector C, what will the resultant of? Look, this was A, this was B. Sorry, this was A, this was B, right? And now I have C vector. So what will be the resultant of this? This vector plus this. So A plus B was there, this plus C. Now I have another vector. So you can simply say the resultant of all will be A plus B plus C. So you can say that if you have this, this, the resultant just basically comes out as uh, the distance from here to here directly, right? This thing. This will comes out as an answer. Could you remember this thing,
Yes.
right? The same concept we are going to here also. How? Let's see. Look, if you see carefully, what is force? You know that force is nothing but you know that in this wire, because of the very small portion, DLN, what is the force on this part? This part is due to some magnetic field that is nothing but DF is equals to I, current is same, right? B is also same, you can say this PF. This is the length, right? Okay, makes sense. So if I ask you what's the net force, I actually don't know. How I'm going to calculate that? Let's see. If I just zoom it out, what you can see is this is the particle here. This is the small length, right? So what is the force on this? This direction. This is your force length. I can actually use some different color for this thing. Yellow. Let's go. It will be very easy. So you can say this is width, right? It will be better to use red color. Here, this kind of vector. At this point, if you reach, it is going this way. This is vector. At this point, 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 this is vector. 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 So if you see, the length has these kind of vectors, right? So ideally, your B is same. Okay, B has the same direction. So can I say that whatever the force direction is going to be, that will be nothing but resultant of all of them, right? Okay, makes sense. This kind of thing you are going to do. So what will be the force? Force will be nothing but F. Uh, F is going to be F1. This is F1, right? L1 basically DL1. DL, the small. Okay, DL plus, sorry, it can be written as DF1 plus DF2 plus DF3 plus DF4. Okay, makes sense. So at the end of the day, because we are calculating force on this wire, can I say that the resultant of this plus this is nothing but this. The whole plus this is nothing but this. The whole plus this is nothing but this. Same this, same this. Okay, I reached it. What about this? This. What about this? This. What about this? This thing plus this thing. So this is the thing. What about this? This was the resultant, so this is the thing. At the end of the day, this is the result. So basically, from wherever you started, from wherever the end, the length of that thing gives you the resultant, right? So here if you see my only variable is b. My only variable is b. Okay. So here if I simply go and say that force will come out as summation of I as it is, b as it is. I just need to do dl. Okay. From where to where my dl is going? The summation of everything goes from 0 to 2. Right? So this answer comes out as IBM. Okay, so it I wanted to say if wire is like this, wire is like this and this, whatever it is, whatever the net starting, what is the this whatever the distance is from starting to ending point, that is going to be electric. That you have to take it as electric. Is that clear? Kitna, is this part clear?
Yes.
Alright. Okay. So yeah, Kitna, that's all for the quiz session. If you have any doubt, please let me know. Otherwise, I will end the session. Okay. Kitna, any doubt?
No.
All right. So I may end this session. Goodbye.